So for the lecture today, we will go through the rest part about the flexible pavement design with the Ontario adaptation, and we want to see what kind of difference between the conventional acetyl method and the MTO adaptation with the acetyl method. So let me start the lecture today. In the meanwhile, if you have any questions, just leave your message in the meeting chat or raise your hand. I will monitor the status of the whole class. Okay. Last time we stopped at the introduction about the serviceability index, and in Ontario we have an additional variable, which is the pavement condition index. It's quite similar to the PSI. Actually, they will represent the same performance of the pavement structure, but they have the different scales. So the PCA can also be applied to identify whether the performance of the pavement is good or not, and at what kind of levels. If it's not good, what's the severity of the performance of the pavement performance. So that's another important variable we have to consider for the when we're designing the pavement in Ontario. And the other thing is about the reliability and the standard deviation. This one's pretty similar to the conventional acetyl method, but they will actually have a little bit different range. For the rows, or most of the rows in Ontario, the standard deviation will be around 0.44 to 0.49 for the flexible pavement. And also there are another variable, another values about the standard deviation with respect to the rigid pavement, which will be covered in the rigid pavement design. The range is between 0.34 to 0.39. And regarding to the design reliability, depending on the type of the road, usually for the major freeways, the reliability should be higher, between 90 to 95%. And if it's a local road, it could be as low as 80%. The range is pretty similar to the acetyl method, but there will be some minor difference. And also there will be some recommended resilient modulus. As we know that resilient modulus is one of the key parameters to estimate the structural number and then to calculate the thickness of the pavement layers. Depending on the types of the materials we applied, for example, for the border or the cobblers, which will be in the very coarse materials, they will usually have a very good drainage system, with drainage characteristics, and does not have any force susceptibility. Then for the resilient modulus, depending on the aggregate distribution, the grain size distribution, we can identify the resilient modulus varies from 70 to 90%, 70 to 90 megapascal. 70 usually indicates the poor performance for the border or cobblers. It could be good condition if the resilient modulus is around 90 megapascal. Also, you can find out the values for the other type of the soils. Basically, in Ontario, we define 8 different classes of the soil, and we have some typical values about the resilient modulus under the poor, fair, and good conditions. In addition, we also need to estimate the coefficients for the structural number. So we want to calculate the estimated values of A1, A2, A3 with respect to the surface layer, the base layer, and the subbase layer. And this table shows the shows the coefficients we're going to use. This one is actually the same to the actual method. So we can find out the value of the alpha1 for the surface layer, for the alpha2 for the base layer, and alpha 3 for the subbase layer materials. And in addition, there's another coefficient which is called the drainage coefficient. Even though it's not applied in the flexible pavement design, but it's still very important. We also need to use this one for the rigid pavement design. So I'll give you a brief introduction about the drainage coefficients. In Ontario, we categorize the drainage coefficients into three drainage conditions: the standard condition, and the questionable condition, and the inadequate condition. Under these three different conditions, you will have different values about the drainage coefficient. At standards 1, and you then gradually reduce them. For the questionable, it's 0.9, and for inadequate, that will be below 0.8. So the table shows the description about the standard, questionable, and inadequate conditions, drainage conditions. You can explore the conditions later by yourself, and it actually depends on the slope we specified, the percentage of the fine particles, and so on. So this is actually we have actually introduced a lot of contents about the drainage system in the previous lectures. And another thing is about the coefficient of the subgrid reaction, which is the K values. This one is only applied for the rigid pavement. We will introduce more details. Actually, for the rigid pavement design, we will focus on analyzing the K values and do some adjustment for the K values. There are also some typical K values for the materials applied in Ontario. Still, we have 8 categories defined, and you can find out the typical K values under the good, fair, and poor conditions for each type of the soil. Again, we will have more descriptions about the K values in the future slides. And the other thing is about the CD, which will be the recommended. It's related to the coefficient of the drainage system, and depending on the weather conditions and the quality of the drainage layers, we can define the ranges of the drainage coefficient. The dry here indicates that the annual precipitation is less than 508 millimeters, and wet indicates that the precipitation is greater than 580 millimeters. And usually the drainage, the quality of the drainage is divided into 5 categories: excellent, good, fair, poor, and very poor. And depending on the climate conditions, you can specify the range for the drainage coefficient. This is actually only applied for the rigid pavement. So we are when we design the rigid pavement structures, we need to refer to this table. And the next thing, which is the most important part, is about the estimations of the traffic volumes and the load, and that refers us to the identify the truck factors in Ontario and the other regions. So the two tables, the table on the left here shows the truck factors applied in Ontario for the which will basically utilize the Ontario truck models. It actually making a summary about the percentage of the truck classes in Ontario, including 2 and 3 axles, 4 axles, 5 axles, and the trucks with more than 6 axles. And it identifies the truck factors. For example, for 4 to 3 axles, the typical value will be 0.4. For 4 axles, it's around 2, and so on. And this is about the truck factor. And we also have the growth factor. Growth factor is something not related to the Ontario rules. It's just a formula, a standard formula that we can calculate based on the annual growth rate. For example, if you are designing the pavement for 20 years, the annual growth rate of 1% represents the growth factor of 22 over the design period. And if it's 5%, that will be 35. This is a very huge increase about the growth of the traffic over the design period. And once you have the track factors, you have the growth factors, you can use the average annual daily traffic, ADT, to calculate the ESAL for the pavement structure. This definition will be the same to all the other even for the AI method and the traditional ASTO method. So basically for the average annual daily traffic, we're going to estimate the traffic for all different classes in Ontario. We're going to consider the vehicle class, 13 vehicle class, and we're going to try to estimate the traffic for all the lanes at different directions. And also, for nowadays, we don't need to do the surveying by ourselves. We will have some automatic traffic recorders like the loop detectors, the cameras to measure the number of the number of the vehicles moving on the road. And we can calculate the average number of the vehicles over the whole year, and then estimate the total number of the volumes over the design period. And regarding to the growth rate, usually it comes from the comparison of the historical annual average daily traffic and the current annual average daily traffic. By finding out the ratios, we will determine the annual growth rate. For the vehicle type distribution, it also comes from the observations, and if possible, we can use the modern technologies to identify the type of the trucks, the type of the vehicles on the road. Generally, in Ontario, we only consider the impact of the vehicle class from 4 to 13. For the first 3 type of the vehicles will be the motorcycles, the passenger cars, the bicycles. Those could be ignored. Their track factor is very small, and it really affect the performance of the pavement. And here there's one example about the calculation of the ESAL on the 2-lane highways, and you can see the how the data is recorded. As we just observed, we will have 13 different type of the vehicles that we have to measure, and the first 3 types of the vehicles, including the passenger cars, motorcycles, and the light-duty trucks, they will be the major portion. They occupy the major portion of the traffic, but as their load is very small, so their load equivalency factor is very small, and usually with the 0 load equivalence factor, the ESAL will be 0. And you can find out the percentage of the other type of the vehicles, like varies from the class 4 to class 13, and by identifying their percentages. For example, in this example, we have the class 5 with 1%, and then the annual average daily traffic is 18,000, and you have the class 6 is also 1%, and class 10 is 0.5%, and so in total would be 100%. With that, you can find out the current annual ESAL, which would be let me see, this would be the column 3 times column 4, and then it shows you the annual ESA. And for the column phi, it actually equals to the value, the current, no, this is not a phi, this should be phi. And the last column, which would be the cumulative ESAL, it will be related to the determined by the value estimated in column 5 times the growth factor. So in this case, that will be 26.87. And with that, you can find out the ESAL for each category of the truck, and then you sum them together. That will be the total number of the ESAL for the design period. So this is about this is one type of the estimation. Oh, I guess I forgot another thing. You also need to time the lane factor. So here is 0.5, and as this is a 2-lane highway, so each direction has one lane, so the direction factor would be 100%. So that's how you're going to get the total ESAL. So that's one example, and we will also have another example to tell you what if there's a significant number of the Trident trucks. That would be the category. That would be category at the class 7. If 2% of the traffic is the Trident trucks, then you can observe that there's a very huge increase about the total ESAL, and that almost more than half of the ESAL are contributed by the class 7, and that's because the load equivalence factor of this one is very high, that is 4.0, and you can see that making a comparison, you can see that for this case the ESAL is around 6.8 million, but for this one it's only around 2.8 million, and the only difference is it's an additional 36,000 Trident trucks moving on the road. So the load equivalence factor is very important. It can significant, even for a small portion of this type of the trucks with a high load equivalence factor, they can still significantly affect the estimation of the ESAL. So that's for the estimation of the traffic. With that, you can then calculate the structural numbers, and then use the structural numbers to estimate the thickness of each pavement layer. So this would be the typical adaptation of the ASTO method in Ontario. But there will be some other advanced construction strategies, which is called the staged construction strategies, staged construction plan. This is applied when the fund is insufficient. What they do is, like in this kind of construction plan, they will divide the whole construction into 2 stages, and in the first and also it's applied at the case when the traffic is the estimation of the traffic is not accurate. Say that the traffic in that region varies a lot. So in that sense, they will split the construction into 2 stages. In the first stage, they will estimate the ESAL for the short period, and then design the road based on that estimation. And after that, they will try to identify the weak spots. The weak spot in the first stage, they're going to observe the weak spot in the first stage, and fix them in the second stage. With that, with these 2 stages, the pavement performance can maintain a high level, and it can last for a longer time. For the staged construction, they have to satisfy this equation. Well, in this equation, the letter n will represent the designed ESAL for the 2 stages, 2 periods, and the N1 and N2 will be the maximum allowable ESALs in the stage 1, stage 2. The staged construction is kind of the new construction method, but it's not widely applied in Ontario. You will only observe some projects in Mississauga, and also this one, even though this one can reduce the budget for the construction, but as it needs multiple constructions, so sometimes it will delay the placement of the surface course. Just let the vehicles moving on the base layers, the emulsified asphalt layers for 1 or 2 years, and does not have any good surface asphalt concrete layers. So not widely applied, but it's just one kind of the method which can be applied, potentially utilized in some other cities in Canada. Another thing I should let you know about is the comparison about the AI method and ASTO method. We know that AI method is an empirical model, and it will use all the historical information, the experience, to design the thickness of each pavement layers. With the ASTO method, which is an MEE method, and is able to estimate the thickness of each pavement layer based on the properties of the materials, based on the traffic load, and so on. So the one of the important difference, like in the ASTO method, we also consider the reliability of the pavement performance and include the pavement serviceability index in the estimation. And it also estimates the effective subgrade soil resilient modulus, which is not the simple average of the pavement structure. Instead, it considers the impact of the climate and the seasonal difference of the resilient modulus. While in the AI methods, the reliability is not considered, and it just applying the constant value of the subgrade resilient modulus, and it could be selected at different percentage, 60% to 60% to 87.5%, depending on the traffic. So with these two differences, the AI and ASTO method will definitely give you a different design results. And this table shows one typical shows some difference about the ASTO method and AI methods. For example, if we have an ESAL about 5.2 thousand, and the thickness of the asphalt concrete layer would be around 5 inches from the ASTO method, but with the AI method, it's only 4.5. And if we have the ESA around 6.8 million, then this asphalt concrete thickness from the ASTO method is 15, from the AI method it's only 14. So there's a slightly different. And another major difference is about the estimations of the effective resilient modulus. With the AI method, you use some percentage. Using some percentage, for example, with this data you collect for all the 12 months, you can find out the resilient modulus of the subgrade soil at every varies over the year. And with the AI methods, say that you can choose the MR as a 60% higher. But with the ASTO method, you need to find out the relative damage the relative damage in each year, in each month, and then find out the average value and convert it back to the resilient modulus. And with that, you calculate the value as 2200 psi compared with the 4500 psi in AI method. This will bring a very huge difference. And that's also the major reason for you to observe the different design results from the actual method and the AI method. Okay, so with that, I think I have finished all the introductions about the flexible pavement design. Do you have any questions about the adaptation, the MTO adaptation about the actual method in Ontario? Again, for the implementation of the actual method, one of the key point is utilizing the normal graph. You have to know how to determine the features of the materials before you implement the normal graph. And then once you have the normal graph, you need to know how to find out the structural numbers, and then use the structural numbers and the coefficient of structural numbers to calculate the thickness of each pavement layer. Okay, any questions so far? Okay, if you don't have any questions, let me try to jump to the next lecture about the rigid pavement design. The design of the rigid pavement will have a lot of similarity to the flexible pavement, and also the actual method it's also can be extended for the rigid pavement design. But in this lecture, we will try to identify the potential difference between the flexible pavement and rigid pavement, and clarify the procedures to design the rigid pavement with the actual method. So this is a, let me try to. This is one typical rigid pavement structure that usually has a PCC slab on the top of the road, and then at the bottom it has the subbase layer to support the PCC slab, and then you will place on the subgrade layer, the subgrade, the natural soil of on the road. There will be a lot of factors we need to consider. So for example, about the tie bar and dowel bars to do the joint, the materials we have to select for the PCC slabs, and the also we need to think about the thickness. Basically, for the rigid pavement design, we will focus on the estimation about the thickness of the PCC slab. So in the design, especially for the consideration of the actual method, we have to consider multiple factors, including the pavement performance, the serviceability index, the traffic volumes and traffic loadings and volumes applied to the rigid pavement, the properties of the subgrade, which would be the road bed, soil and the slab characteristics, the environmental impact, the reliability, the life cycle cost, and the also some, if necessary, we should also consider the shelter design to support the rigid pavement. But in this class, we will focus on the first 5 factors, which will be the most important factors we need to apply. So regarding to the rigid pavement, we have different type of the rigid pavement. The joint plain concrete pavement, we have the joint reinforcement concrete pavement, the compressed reinforced concrete pavement, and so on. The design procedure will be very similar to the flexible pavement. It also has the normal graph for you to identify the actually for you to estimate the thickness of the PCC slabs. the target is trying to find out what's the thickness of the slab under the specific traffic loadings, the specific properties of the PCC slab. And we need to do some iterations to make sure that the estimation is accurate enough. But I will give you more details about how we're gonna go through the design with the Ashton method. This figure shows the relationship between the designed traffic load with respect to the properties of the rigid pavement, and we have this equation for the flexible pavement, but you will observe different coefficients applied for the rigid pavement. Basically, in this in the rigid pavement design equation, the designed ESAL is a function of the reliability and the standard deviation and the reliability of the pavement, the thickness of the pavement layer, the changes in the or the serviceability index loss, the values of the terminal serviceability, the modulus of the rupture, the drainage coefficient, load transfer coefficient, modulus of the elasticity, and modulus of the subgrid reaction. So there will be more variables we have to consider compared with the flexible pavement. So let's go through them one by one to see their definitions and then see how we can use them in the normal graph. First of all, for the rigid pavement, we have introduced these slides in our when we go through the stress and strain analysis. We can see that for the stress and strain analysis of the rigid pavement, we will assume that the PCC slab is linearly elastic, and for the unbound layer, which would be base or the subgrade layer, they also have the linearly elastic properties, and we can assume them as the wrinkler springs so that we can apply the slab actions to determine to estimate the stress and strain from the rigid pavement. This will also be applied. This will also be applied for the rigid pavement design. This is one of the major difference from the flexible pavement. So for the rigid pavement design, the core factors we have to estimate is the coefficient of the subgrade reaction. That will be the variable K. We have introduced the definitions of the coefficient of subgrade reaction a lot in the previous lectures. We said that it's not the it's not a physical feature of the soil. Instead, it depends on a lot of in situ conditions. The K could be affected by the moisture contents and the density of the soil, which will be related to the compaction levels. And if we are not estimating the K values from the plate load test, you can also estimate the value of K from the CBR or MR. And in the rigid pavement design, we need to use the K value, the estimated K value, to find out the composite K value, which will be the combined K value for the subbase layer and subgrade layer. And also we're going to use the composite K value to estimate the effective K value, which will take the consideration of the seasonal variations. The K values will be different at the different seasons of the year. And this procedure will be very similar to the flexible pavement. I'm going to show you how to do this kind of adjustment, how to get the K value from calculate K value, calculate the composite K value, and convert them to the effective K value. This table shows some typical K values applied for the for three different type of the soils, the subgrade soils, depending on their qualities. For the low quality subgrade soil, where they have a lot of fine particles, the K value would be around the 20 to 34, and which will be related to the CBR value of 2.5 to 3.5. And if we have the a lot of sand or the sand and gravel mixtures, then the support of the base layer, sub-base layer, or the subgrade layer to the PCC slab will be high, and the K value would be around 50 to 60 megapascal per meter, and the CBR will be around 8.5 to 12. So that will be the typical K values. We are that's the definition of the K values, and in the design we also need to know the elastic modulus. For the rigid pavement, especially for the concrete slab, the elastic modulus cannot be estimated directly. Instead, it can be estimated based on the compressive strength. And once we have determined the compressive strength, we can use the several equations. If we have the unit of the elastic modulus of gigapascal, then the EC will be 4,730 times the square root of the FC in gigapascal. You can also use the second equation to calculate the elastic modulus in PSI directly, and also there's another equation to find out the elastic modulus as a function of the compressive strength and the unit weight, which will be the density of the concrete slab. So those will all be the possible equations that you can apply. But in general, we're going to use the lab experiment to find out the compressive strength of the PCC slab, and then estimate the elastic modulus. And another factor we have to consider for the concrete slab is the flexural strength, which is also called the modulus of the rupture. And this one is also the function of the compressive strength. You can either apply the first equation to get the modulus of the rupture in the unit of the megapascal, or you can get the second equation to find out the value under the unit of PSI. So either way is fine. So those would be, this is another variable you have to apply for the, to consider for the concrete slab. And this figure actually shows the relationship between the modulus of the rupture with respect to different compressive strengths. This is actually applied to different in this figure, you can actually see different lines, different equations that I showed in the previous slides. That actually comes from different researchers and different lab experiments. Basically, you will observe the increased modulus of the rupture under the higher compressive strength for the PCC slab. You don't need to explore the details about how those lines are fitted and how the data are collected. Just understand the general trend and know how to use the equation to calculate the modulus of the rupture, the modulus of the elasticity with the compressive strength. And the next thing we need to think about for the rigid pavement design is the traffic analysis. Well, basically the traffic analysis for the rigid pavement design will be almost be the same to the flexible pavement design. There will be some slightly difference about the load equivalency factor. I'll go through them later. Here I've just given a quick review about the calculation of the ESAR based on the annual average daily traffic, the truck factor, the percentage of the truck, the truck factors, the number of the days, the growth factor, the distribution factor, land distribution factor, and so on. This is the same as what we learned previously. But the things we want to think about is we want to identify is the load equivalency factor. the actual load equivalence factor for the rigid pavement and the flexible pavement are very different. And this table shows the some typical load equivalence factor under the flexible and rigid pavement, depending on the type of the axials and the space between the axials. So if we take the one example, for example, for the tandem axial with zero spacing, and you can see that the load equivalence factor for the flexible pavement is only 13.9, but for the rigid pavement is much higher. That will be around 18.3. So this difference will actually cause the different different values of the different estimated values of the ESAL for the rigid and the flexible pavements. And here you can see some more comparisons between the flexible and the rigid pavement. For the single axle and tandem axle, depending on the different axial load, you can find out the values of the load equivalence vector. But basically, you're going to follow the similar trend. When the load is very low, we will almost does not see any the load equivalence factor would be very small and does not see any impact about the vehicles, the traffic with low with smaller load to the total ESAL. But if there's a small, even if there's a small portion of the truck with a heavy load and a large LEF, they can still significantly affect the estimation of the ESAL. You can refer to this table for the estimate for the estimation of the ESAL with respect to the flexible and rigid pavements. And again, you need to consider that this one only applies for the terminal serviceability of 2.5 and the structural number of 3.0 for the flexible pavement, and the slab thickness of 9 inches for the rigid pavement. So this would be the conditions for you to use this table. And this is actually only applied for the road in Ontario. And here we will have more examples about the load equivalence factor for the rigid pavement with the thickness of 9 inches and terminal serviceability of 2.5. You can find out the axial load in kilopounds and locate the value of the LEF with respect to single, tandem, and trident axials. So this is some typical values we're going to apply in the AASHTO method. And in Ontario, we will also refer to the definitions of the vehicle classes from the FHWA. There will be 13 different classes of the vehicles, and you can find out the typical truck factors for the rigid pavement. This is for the rigid pavement. And once you have the average annual daily traffic, the growth rate, and also the load equivalence factor, you will be able to estimate the ESAL. The process is very similar to the flexible pavement, but the value you estimate will be very different. Even with the same amount of the vehicles, same amount of the trucks with the same load, the estimated ESAL in the rigid pavement will be different from that in the flexible pavement. And this is because the response of the pavement is to the same load in the rigid and the flexible pavements are different, and we have different load equivalence factors. So this is another equation for you to estimate the load equivalency factor. It actually comes from the empirical data With this one, you can calculate the load equivalency factor. This from here, LEF, as a function of the load in the under the x-axis and the load within the tendon axis, and also the values of GT and GX, which will be related to the load, the depth, and the terminal serviceability. We actually introduce this one in the topic in the chapter when we go through the stress and strain analysis. You can go back to those lecture and see how we're going to use the equations to calculate the LEF values. Here would be more descriptions about the variables applied in the previous equations. You should pay attention to the two factors. Lx is the load in kilopounds for a single axial, and on one single axial, one set of tendon axial, or one set of the trailing axial, and the L2 will be the axial code, would be 1, 2, and 3 to represent the different axial structures. And another thing I would like to further introduce is the how the rigid pavement is designed with respect to the agitator methods. Actually, the whole design is based on the distress criterions, which is similar to the flexible pavement. In the rigid pavement, we will only need to consider two types of the distress. The first one is the fatigue of the concrete slab. It could be it will occurs at the pavement structure and cause some cracking or even the functional failure to the pavement. And the second type of the criterion we have to consider, or distress we have to consider, is the erosion of the subgrade soil, which would be the subgrade layer. And we will usually consider the mud pumping. Actually, we have introduced the mechanism of the mud pumping in the previous lecture, and this kind of failure will usually occurs at the joint of two PCC slabs. And we're going to introduce more details about how this kind of distress of the rigid pavement will be applied, and how we're going to use them to design the pavement layers, to estimate the thickness of the PCC slab. Okay, I guess I don't have enough time to go through the details about the design criterions. I will continue this lecture in the next, in the lecture tomorrow. And well, do we have 1 minute? Do you have? I want to reserve this one for the questions. Do you have any questions about the lecture? I know that this is for this lecture there will be a lot of concepts. It's a kind of basically this kind of design. The rigid pavement design is very similar to the flexible pavement design. I pick up them to just go through the all the general variables you're going to apply it. Most of them has already been defined in the flexible pavement design. So I go through them very quickly, and later on, once we introduced all the variables, you will be able to quickly estimate those variables and apply the normal graph to do the estimation. Okay, do you have any questions for now? Okay, if you don't have any questions, I believe that will be all about the lecture today. And just giving the reminder, like we will finish all the lectures tomorrow, and in the lecture For the lecture on Monday, we're gonna have the final review session. And also tomorrow, I plan to set up our last in-class questions and give you some ideas about how the flexible pavement or the rigid pavement is designed. Okay, I think that'll be all. Thank you very much for your time. And with that, I will close the meeting today and see you tomorrow.